Okay, so welcome back to this next video in which we are discussing cholesterol biosynthesis. Okay, right, so we will continue the pathway in this video, and we had got to the stage where we have produced HMG-CoA. And remember, HMG-CoA was short for beta-hydroxy, so that was what the H was for, that was for the beta-hydroxy, and then it was beta-methyl, so that's the M, and then we've got glutaryl coenzyme A, so the G is for glutaryl, and then we've got a coenzyme A molecule attached onto that. Okay, so basically glutaric acid is a 5-carbon molecule where you have carboxylic acid groups at either end. Okay, and then the beta-hydroxy beta-methyl means that you have a hydroxyl group coming off the middle carbon of that glutaric acid molecule and a methyl group coming off also the middle carbon. And then finally you've got a coenzyme A molecule on one side. So let me show this. So we'll start off by drawing 5 carbons, 1, 2, 3, 4, 5, okay? And then on the carboxylic acid group on one side, what you'll have is a coenzyme A molecule bound via a Phosphoester link, okay? Then off the second carbon, you'll have 2 hydrogens, so that's just a methylene group. Then this third carbon is important. This is the one off which the hydroxyl and the methyl group come. So we've got a methyl group coming off this middle carbon and also an alcohol group coming off that middle carbon. Then off the fourth carbon we have 2 hydrogen atoms. Okay, and then finally the 5th carbon is also involved in another carboxylic acid group. Okay, so glutaric acid is a double-ended carboxylic acid, if you like. Okay, right, so this is the structure of beta-hydroxy beta-methyl glutaryl CoA, and this carboxylic acid group will be deprotonated under physiological pHs. Okay, right. The next reaction is an extremely important one because this is the rate-limiting step for the entire biosynthesis of cholesterol. It's also the site of action of the drugs, statins, which are incredibly successful drugs which block the de novo synthesis of cholesterol by blocking the enzyme which catalyzes this next reaction. So this next reaction is catalyzed by the enzyme HMG, so beta-hydroxy beta-methyl glutaryl CoA, and then it's HMG-CoA reductase. Okay, right. So basically, this enzyme is blocked by the statins. Okay, examples of which are simvastatin, rosuvastatin, atorvastatin. Okay, so simvastatin is a good example of a statin. You've also got atorvastatin, which is one of the greatest selling drugs ever. Okay, and then another example is rosuvastatin. Okay, so they all have names which end in statin. And it should be rosuvastatin. Okay, right. So all of these drugs work by blocking this enzyme HMG-CoA reductase and thereby blocking the conversion of HMG-CoA into whatever we're about to convert it into, which is an essential step in the production of cholesterol de novo. Okay, so what are we about to turn HMG-CoA into? Well, basically we're about to turn it into mevalonate. Okay, and to do this, what we need is 2 molecules of reduced NADP. Okay, so here come in our 2 molecules of reduced NADP, and remember those both carry hydride anions. In addition, we're also going to need 2 protons. So if we've got 2 hydride anions and 2 protons, that means overall we're bringing in effectively 4 hydrogen atoms, because you can imagine these 2 hydride anions giving up their additional electron to these 2 protons to make overall 4 neutral hydrogen atoms. Okay, and the output will be 2 oxidized NADP molecules, like so. Okay, so what are we going to do? Well, the first thing that we're going to do is we're going to break this Phosphoester link here. Okay, so you can imagine giving 1 electron in this Phosphoester link back to the carbon and 1 back to the sulfur atom. Okay, and then bind a hydrogen onto the carbon and bind a hydrogen onto the sulfur atom. And what that will recreate for you is a coenzyme A molecule with an intact thiol group. So here is a coenzyme A molecule with an intact thiol group. And then we've also got a carbon with a hydrogen coming off it, and that gives us an aldehyde group here. Okay, then we're not going to stop there. We've used 2 of these hydrogen atoms now. We can go further. We can break the second of those 2 bonds between the carbon atom and the oxygen atom. And if you do that, you can imagine sending 1 electron back to the carbon and 1 back to the oxygen. Then bind these 2 other hydrogen atoms that we've got to the carbon and to the oxygen. So bind 1 to the carbon and 1 to the oxygen. And overall, what we're going to end up with then on this carbon is we'll have 2 hydrogen atoms coming off this carbon, and then we'll have an alcohol group coming off this carbon. So we'll end up with a primary alcohol group. Okay, right, so let's show this. So most of the molecule remains unchanged. So we still have this carboxylic acid group down here. We then have our second carbon down here. Okay, then the middle carbon here with an alcohol group on it, and a methyl group here. Then we've got a methylene group here, and now this final carbon now is in the form of an alcohol group here, which has got 2 hydrogens coming off it, like so. Okay, so that is the structure of the molecule mevalonate. Okay, and the naming of the carbons now completely changes. We will consider this the first carbon, because that's the one in the carboxylic acid group now. We'll consider this one the second one, this one the third one, this one the fourth one, and this one the fifth one. Okay, so now what we're going to do is we're going to work with mevalonate. We're going to start adding phosphate groups onto mevalonate, and we're going to convert mevalonate into what are known as activated isoprene molecules. Okay, and I'll explain what that means when we get there. Okay, so we have now completed the first stage in cholesterol biosynthesis. The first stage is taking in 3 acetyl coenzyme A molecules and forming a mevalonate molecule. We're now going on to the second stage, okay, if you like, step 2, which is basically going to be converting these mevalonate molecules into activated isoprene molecules. Okay, so let's now have a look at step 2. So, we're going to start off by adding on a phosphate group onto the alcohol group that comes off the 5th carbon of the mevalonate molecule, okay, to create us 5-phosphomevalonate. Okay, so let me show you what we're going to do. Basically, we're going to nick the phosphate group off an ATP molecule and add it onto the mevalonate molecule to create 5-phosphomevalonate. Okay, right, so ATP will go to ADP, and it will therefore lose its final phosphate group, and we will transfer that phosphate group onto our mevalonate molecule here. Okay, right, so let's draw what we will get then. So the first carbon of mevalonate is completely unchanged, so it's still in its conjugate base form of the carboxylic acid group. Okay, and then we've got our methylene group here. Then our third carbon has a methyl group coming off it, and also an alcohol group coming off it. Then the fourth carbon is just in a methylene group, like so. And now this 5th carbon is going to have a phosphate group coming off that alcohol group. Okay, so we're going to attach the phosphate group on via what's known as a phosphoester link. So I suppose I should just tell you, show you what a phosphate group actually looks like. So basically, when people normally talk about phosphate groups, they usually mean inorganic phosphate groups. Okay, so let me show you an inorganic phosphate group. So basically, an inorganic phosphate group has a phosphorus atom at the center. Then this phosphorus atom has an oxygen double bound to it, like so. And then coming off the phosphorus atom, we also have 2 alcohol groups. And then we also have an oxygen singly bound to this phosphorus atom. And this oxygen has then acquired its final electron to make up the 8 in its outer shell via ionic means, and therefore has a negative charge. So this is the structure of a phosphate group. Now basically you combine phosphate groups to alcohol groups in much the same way that you combine carboxylic acid groups to alcohol groups. Because if we look at this group that I have just circled in red here, Okay, so if we just look at the phosphorus atom double bound to an oxygen with an alcohol group coming off, that looks awfully like a carboxylic acid group. In fact, if I replace that phosphorus atom with a carbon atom, then that would be a carboxylic acid group. Ignore the fact that it's got overall 5 bonds coming off it, which is obviously absurd for carbon. Okay, but this group that I've circled in red would look like a carboxylic acid group. So basically what can happen is you can react this phosphate group with an alcohol group in much the same way as you would a carboxylic acid. Whoops, not like that. Okay, so you take the alcohol group off the phosphorus atom, you then take the hydrogen off the alcohol group, like so. You'd bind those two things together in this contorted manner to produce water, okay, and you then bind the phosphorus atom to the oxygen atom of the alcohol group there to create what's called a phosphoester link. Okay, so it's very analogous to an ester link, except that instead of using a carboxylic acid group, we have used a phosphate group. So this is a phosphoester link. Okay, so that's what we're effectively going to do here. So we'll have a phosphorus atom here, double bound to an oxygen, and then we'll have an oxygen with a negative charge, which is this one down here. And now this alcohol group will generally lose its proton under physiological pH, so it will generally be present like so. Okay, now, this molecule that we have created here is known as 5-phosphomevalonate. Okay, now when we attach this phosphate group onto mevalonate, we don't get it from just an inorganic phosphate group floating around the cytoplasm. Instead, we nick the phosphate group off ATP and add it onto the alcohol group of the mevalonate molecule. Okay, so this is 5-phosphomevalonate. Okay, whoops, there we go. And the enzyme which catalyzes the conversion of mevalonate into 5-phosphomevalonate is mevalonate 5-phosphotransferase. Okay, so this enzyme here is mevalonate 5-phosphotransferase. So we are transferring onto the mevalonate a phosphate group that will be on the 5th carbon. So this is mevalonate 5-phosphotransferase. Okay, and phosphotransferase should all be one big word, but I don't have room to write it all in there. So mevalonate 5-phosphotransferase. Right, so we've now got to 5-phosphomevalonate. Okay, the next step is we're going to add another phosphate group onto the 5-phosphomevalonate. Okay, and we're going to add this onto the phosphate group that we've already got here. So this phosphate group effectively has an alcohol group here. So what we're going to do is take another phosphate group and link that onto the alcohol group of this phosphate group via a phosphoester link. Okay, right, so let's show this. So again, we're going to source our phosphate group from an ATP molecule. So we're going to hydrolyze ATP, okay, to ADP, and that phosphate that we get, we're just going to transfer it onto the alcohol group here. Okay, right. What we're going to end up with then is the mevalonate molecule now with 2 phosphate groups added onto the ends. Let's draw this. So here's our carboxylic acid group still in the conjugate base form. Here's the methylene group, here's the middle carbon which has a methyl group coming off it and an alcohol group coming off it. Then we've got another methylene group here. Okay, another methylene group which will then have an alcohol group coming off it which is involved in a phosphoester link to this first phosphate group, and now we have another phosphate group linked off that first phosphate group like so. Okay, and again, both of these oxygens will generally be in the negative form where they've lost their protons under physiological pH. Okay, so this molecule that you've now got here is called 5-pyrophosphate. Okay, so 5-pyrophosphomevalonate. So you've got a pyrophosphate molecule effectively added on to mevalonate. So 5-pyrophosphomevalonate. Okay, so pyrophosphate means 2 phosphate groups bound together like so. This is pyrophosphate. So this is 5-pyrophosphomevalonate. Mevalonate with a pyrophosphate molecule bound to the 5th carbon's alcohol group. Okay, right. The enzyme which adds that additional phosphate group onto 5-phosphomevalonate is phosphomevalonate kinase. Okay, so this is phosphomevalonate kinase. So enzymes which add phosphate groups onto molecules are called kinase enzymes. So this is mevalonate. So phosphomevalonate kinase. So this is adding a phosphate group onto phosphomevalonate. Okay, right. Now we're going to add a third phosphate group onto this 5-pyrophosphomevalonate now. Okay, and this time what we're going to do is add it onto this alcohol group that comes off the third carbon here. Okay, now this will form an intermediate that then is going to go on to be catalyzed by the same enzyme into a further structure. Okay, so the next reaction that we're going to look at, the enzyme is going to catalyze 2 steps basically. It's going to firstly add a phosphate group onto here, and then it's going to remove this carbon carboxyl group here from the 5-pyrophosphomevalonate molecule. Okay, so basically the next enzyme that's going to do all of this is called pyrophosphate mevalonate decarboxylase. Okay, so the next enzyme along is pyrophosphate and then mevalonate decarboxylase. So pyrophosphate mevalonate decarboxylase. And the first reaction that this pyrophosphate mevalonate decarboxylase is going to catalyze is it's going to catalyze the addition of another phosphate group onto that alcohol group that comes off the third carbon of the pyrophosphomevalonate molecule. Okay, right, so let's draw all of this then. So the first thing that you're going to do is add on another phosphate group. So let me draw the product. Okay, so we're used now to the idea of adding a phosphate group onto an alcohol group. So here's our carboxylic acid group, which for now is still intact. Then off our third carbon, we still have our methyl group coming up here, but off this alcohol group, we're going to have a phosphate group now linked. And remember, as always, this phosphate group generally under physiological pH will have lost both of its protons, and therefore we'll have these 2 oxygens now with negative charges. Okay? Then off the 4th carbon we have 2 hydrogens, and then the 5th carbon, we know what we've got here. We've got our pyrophosphate molecule linked off the alcohol group off the 5th carbon. Okay, so here is our first phosphate group here. Then we have our second phosphate group here. Okay, like so. Right, so this molecule here is known as 3-phospho-5-pyrophosphomevalonate. Okay, so 3-phospho, because we've got a phosphate group coming off the third carbon's alcohol group now, and then we've got 5-pyrophospho, because we've got a pyrophosphate group coming off the alcohol group at the 5th carbon, and then mevalonate, and it should all be one word, but I can't fit it in there. Okay, so this is 3-phospho-5-pyrophosphomevalonate, and basically this enzyme, pyrophosphate mevalonate decarboxylase, will catalyze this first reaction by nicking the phosphate group that it's about to add on to the 5-pyrophosphomevalonate from ATP and sticking it onto the alcohol group that comes off the third carbon of the 5-pyrophosphate mevalonate. Okay, right. So that name of that enzyme doesn't seem to fit though, decarboxylase. We haven't seen anything like that. So it's now going to catalyze the next reaction. So this is an intermediate basically. It doesn't stop there, it's going to convert it further into what's known as delta-3 isopentenyl pyrophosphate. Okay, right. So what's going to happen is we're going to remove this carboxyl group here. Okay, so what you can imagine doing is breaking this bond here between this carbon and this carbon and give this time both electrons back to that carbon there. Then this oxygen, which has a negative charge, which means that it has a lone pair of electrons, and in that lone pair one of the electrons is not actually from the oxygen, it doesn't belong to it. Okay, what it's going to do is it's going to use that lone pair of electrons to form a single bond, another single bond, between itself and this carbon. And when it does that, it will effectively give one of those electrons to the carbon, and therefore it will neutralize the positive charge that the carbon will have once we've taken one electron from it by giving both of the electrons in this bond to the carbon, even though one originally belongs to this carbon over here. Okay, right. So what you will then get being produced is a carbon dioxide molecule, so carbon double bound to these two oxygens. Okay, then what we've got is this carbon here with a negative charge now. Okay, what we're going to do is we're going to also break this bond here. And again, you can imagine giving both electrons back to this oxygen here. So send both electrons back to the oxygen. One of the electrons belonged to the oxygen, so that's fine, but the other didn't. The other belonged to this carbon. So the oxygen has therefore gained an electron via that, and will now have a negative charge. What you're then going to do is bind this carbon here, which has those two electrons, which are giving it a negative charge, to this carbon here. So you're going to make another single bond between this carbon and this carbon to turn that single bond into a double bond. Okay, so what you're going to end up with is carbon double bonded to carbon, and then you'll have two hydrogens coming off it, like so. Then you'll have a methyl group coming off this carbon also. You've no longer got this phosphate group coming off, so this will now go off, and it will most likely get protonated. I mean, it's not going to remain with 3 negative charges. One of those, at the very least, one of them will end up getting protonated, if not 2. Okay, just from the solution. But we're not bothered about that phosphate group now. Okay, and then we've got these 2 methylene groups here, so an ethylene group, if you like. And then off this last carbon over here, we've got the pyrophosphate group linked on here. So here we go. That's the first phosphate, and then linked to it via a phosphoester link, we have another phosphate group here. Okay, right. So this molecule that you have now created has the rather fantastic name delta-3, and then it's isopentenyl, and then pyrophosphate. So isopentenyl and then pyrophosphate, 2 separate words. So that's the full name for this molecule. And this reaction where we convert the 3-phospho-5-pyrophosphomevalonate into the delta-3 isopentenyl pyrophosphate is again catalyzed by pyrophosphate mevalonate decarboxylase. So pyrophosphate mevalonate decarboxylase is going to catalyze this this reaction again. Okay, now this product that we are seeing here, this delta-3 isopentenyl pyrophosphate, this is our first example of an activated isoprene. Okay, however, it's not the only activated isoprene we need. We need another one. Okay, and this luckily can be made from this delta-3 isopentenyl pyrophosphate. Okay, so there is basically a reversible reaction now between isopentenyl pyrophosphate of the delta-3 type and another structural isomer of it, which is known as dimethyl allyl pyrophosphate. Okay, so basically to create dimethyl allyl pyrophosphate, all you need to do is break the second of those 2 bonds between these 2 carbons here, and imagine giving 1 electron back to each member. Then break one of these single bonds between this carbon and this hydrogen here, give 1 electron back to this carbon and 1 back to this hydrogen. Bind this hydrogen, which has a free electron, to this carbon over here, which has a free electron, to create a methyl group over there, and then bind this carbon to this carbon. Okay, because they both have free electrons from the breaking of this bond and the breaking of this bond. Okay, so what you'll overall end up with then is a methyl group on the end here. Then you'll have this carbon here with a methyl group coming off it, a double bond in the middle, which has a single hydrogen now coming off it, and then a methylene group finally, with then a pyrophosphate group sticking off it. Okay. So here is the first phosphate of the pyrophosphate group, and here is the second phosphate of the pyrophosphate group, like so. And this molecule is called dimethyl allyl pyrophosphate. Okay, and it is also an activated isoprene, and I will explain to you in a moment what it means to be an activated isoprene. Okay, because basically these are the two molecules now which we are going to use to make cholesterol, and basically they are based on the structure of a molecule called isoprene, and we can now polymerize them together to make the cholesterol molecule. Okay, so the enzyme which converts delta-3 isopentenyl pyrophosphate to dimethyl allyl pyrophosphate, which is a reversible reaction, is an enzyme known as isopentenyl pyrophosphate isomerase. Okay, so isopentenyl pyrophosphate isomerase. Okay, and for short, isopentenyl pyrophosphate is often abbreviated to IPP, for I for isopentenyl, PP for pyrophosphate. So you might just call this IPP isomerase rather than isopentenyl pyrophosphate isomerase. So this is catalyzing this reversible reaction here, which converts delta-3 isopentenyl pyrophosphate into dimethyl allyl pyrophosphate, and then dimethyl allyl pyrophosphate back into delta-3 isopentenyl pyrophosphate. Okay, right. So both of these molecules now are what are known as activated isoprenes, and this is stage 2 now of cholesterol biosynthesis finished, because we have created the activated isoprenes, which are the things we are going to need to make cholesterol. So let me just explain to you what isoprene actually is. So basically, you will see that these structures all have isoprene within them when I show you the structure. Well, not quite, maybe not quite, but they've got a structure that's based on isoprene. They've got the activated form, if you like, within them. Okay, so basically, isoprene consists of a main 4-carbon structure, where you have a double bond between the first and second carbon, and a double bond between the third and fourth carbon, and then you've got a methyl group coming off the second carbon here, like so. Okay, and then just saturate everything else up now with hydrogen. So you'll have a hydrogen there, a hydrogen there, a hydrogen there, and a hydrogen there. This is an isoprene molecule. Now basically you can polymerize isoprene molecules together to make a huge great polymer. Okay? Now these structures are basically the things which you can use to polymerize together, basically. That's what's meant by an activated isoprene. An isoprene molecule that is actually ready to be polymerized together. Okay? Because to polymerize isoprene molecules together, what you have to do is break this bond here, break this bond here. So break one of the 2 bonds in those double bonds. Not both of them. Leave one of the covalent bonds. Just break one of them. Okay, then imagine returning 1 electron to each of the carbons within the double bond. So return 1 electron to this one, 1 electron to this one, return 1 electron to this one, 1 electron to this one. And then bind these 2 carbons in the middle together now to create a double bond in between them. Okay, because they both have 3 electrons from the breaking of these 2 bonds on the either side. And then what are you left with? Well, let me show you what you're left with. So here is our main 4-carbon structure here. We've got our methyl group coming up here. We've got our hydrogen coming down there. And now each of these carbons on the side has got still 2 hydrogens bound to it, but then has got a free electron as well. Okay, each of them. Now if you imagine having loads of these molecules, can you see the potential for what you can do? If we had another one of these molecules here now, okay, so let me bring another one like so. So we have our double bond in the middle, a hydrogen off this carbon, and then our methylene group on the side. And again, both of these carbons on either side will have free electrons. Well, basically what you can do is you can form a bond between those 2 carbons, okay? and you've now joined those two isoprene molecules together. And then what you can do is bring another one of these molecules and bang it on over here, another one and bring it on over here, and you can keep going and polymerize and polymerize and polymerize and produce a huge great polymer of isoprene molecules. Okay, now of course it's not as simple as just dumping a lump of isoprene into a solution and hoping that it will react and form you a nice polymer. In reality, the actual steps that are needed are much more complicated. So firstly, what you have to do is produce these activated isoprenes, which are isoprenes that are actually ready to react with one another and polymerize. But this is the basic principle of how you're going to bind isoprenes together to make bigger structures. Okay, and hopefully you can see that this has something that's very similar to an isoprene molecule in it. Yes, it's got this pyrophosphate sticking off the side, but that's going to go. Okay, in addition, this is also very similar to isoprene, and again it's got the pyrophosphate sticking off it. So these are the two molecules now which we are going to use to make cholesterol. So we have now got a plentiful supply of delta-free isopentenyl pyrophosphate and also dimethylallyl pyrophosphate. And we now want to see how we're going to bind them all together to make cholesterol.